This is my circuit. This is to represent a sound output from a hearing aid, which completes to be a biomedical signal processing system. I'll be explaining the different parts in stages. In stage 1, IC1A, which is TL072, is a dual low noise JFET input general purpose operational amplifier. It does not provide current but supplies voltage to the circuit. The op amp amplifies the sound, where sound can be added or subtracted. Based on this circuit, it is a closed loop, non inverting op amplifier. Hence, the circuit needs to convert the electrical microphone level up to a level suitable for a line input. The capacitor C1 at 10 microfarads blocks the DC bias voltage from the input. The voltage divider consists of two 10 kilo ohms resistors, and they supply half of the voltage. Hence, supplies the op amp to be working at a single supply mode, which is 4.5 volts. For capacitor 2 and 3, as well as resistor R2 and R3, they form the band pass filter. The pass band is 1 plus bracket 22,220 over 10 kilohertz, which is equal to 23. For capacitor 4, at 10 microfarads, results in the output from the first amplifier. Hence, if any DC input offset were to be applied, it causes a larger output offset, which its waveform will be cut. Hence, capacitor 4 passes out AC signals while blocking DC signals. Let's take a look at the results. So as we can see, as the frequency increases, the gain will also increase until its maximum is at 24, which is shown. Its frequency will be at 100 Hz. If it's more than 100 Hz, voltage gain will start to drop. Hence, the gain at 24 will be 27.60 decibels. As we can see from the graph, alright, so basically my highest point, which will be 27.60 decibels. If we minus 3 decibels, you'll get 24.60 decibels. From there, we can find the FH and the FL. So as you can see, my FH is 1700 and my FL is around 20. Yeah, so from here, we can find the bandwidth, which we minus FH and FL. To test the circuit, we will set the power supply to 9 volts and connect it to the circuit. Hence, the function generator will be set at 1 kHz and at 200 mVpp. Then put the channel 1 probe at TP1 and channel 2 probe at TP2. This will give us an output voltage of 3.52 volts. In stage 2, for the IC1B, it's the same as the previous stage by sharing the same IC TL072. It is a negative feedback loop amplifier. Negative feedback loops is basically whereby a portion of the output voltage of an amplifier is returned to the input with a phase inversion, also known as 180 degrees out of phase. Hence, the trimmer controls the feedback signal that can reduce the overall gain of the amplifier, which functions as a linear amplifier and will not saturate the output voltage. Resistor 9 and resistor 10 are level shifters that shift the waveform and that the output will not be clipped. Next, connect the channel 1 probe to TP2 and channel 2 probe to TP3. Hence, we get output of voltage of 6, and as I adjust the trimmer, the waveform will be amplified and at some point, it will be saturated and cut off. In stage 3, capacitor 5, which is 10 microfarads, will block out the DC and allow AC to pass through. A voltage divider, which is resistor 11 and 12 of 10 kilo ohms, acts as a single supply mode for the second IC TL072. It also works as a level shifter to make sure no output is clipped. For IC2A, another TL072 is used. It is patched as a Cellen key second order low pass filter and made out of two low pass RC networks. Capacitor 7 will provide the feedback for shaping the response near the edge of the pass band. It allows low frequency to pass through while filtering out the high frequency. Output voltage from ICA2 will then be passed through capacitor 8 to filter out any DC. Okay, from here, basically, if you want to find FH, FL is 0 Hz. Hence, FH is equal to FC because the bandwidth, which is FH minus FL, you get FH minus 0 to get FC. Okay, so basically, to find what is our to find what is F, you will basically use all of the values given to us in the circuit respectively. From there, we will apply the formula and you get 995.925 and then you round up to get 996 Hertz. Okay, so this is the trend. Basically, as the frequency increases and with my V in being constant, you can see that V out starts to change and the voltage drops. And same thing for the voltage gain, which will also drop. And hence for our AV, it will also basically drop into the negatives. And my highest in the end will be negative 0.35. Okay, from here we can derive from the graph that FH is equal to 200 Hz. Bandwidth is FH minus FL, hence 200 Hz minus 0 Hz, you get 200 Hz. You will connect the channel 1 at TP3 and channel 2 at TP4. Hence, you'll get a filtered output voltage of 4 volts. As you can see from the weight generator, as you can see, it is below 500 Hz, it will have a unity gain. This is another reading with different values. In the final stage, IC LM386N1 is being used. It is an audio amplifier that drives a speaker. It is designed to be working in a single supply mode, hence no additional voltage divider is required. It is the only amplifier that drives current to power up the speaker. Capacitor 15 filters out the high frequency that is above 40 kHz. Without it, output voltage will be slightly unstable. C13, also known as capacitor 13, will block out DC and allow AC to pass through. Pin E will have a full amplitude, whereas for pin A and S, we will have a zero amplitude. Channel 1 port will be connected to TP4 and channel 2 port will be connected to TP5. We will then get an output of around 7.2 volts. By adjusting the trimmer at TP5, we can control the output. Hence, the final output waveform can be attained without the waveform being saturated.